I hope you can read this, all of you.
Yes. Yes, sir.
Now please try and understand. After the Bohr atomic model, still we have to discuss that. I am showing you these excerpts because in chemistry you have learned up to Schrodinger's equation, correct? So you must not have confusion with all these models, because as I keep telling you, when the question is pertaining to Bohr model, you should take into consideration all those things that are discussed in Bohr, and that only you should discuss. With that in the framework, you should answer the questions. Okay. However, I am showing you all this because you should get a proper link to whatever you have learned and whatever you have learned so far in physics and whatever you have already learned in chemistry. Okay. So I am just giving you the link quickly. So according to classical mechanics, that is Rutherford Bohr atomic model, an electron should revolve in a circle around the nucleus. Now I am making it explicit. According to this model, it should revolve in circle around the nucleus. It is apparent that this model is not entirely accurate when applied to atoms other than hydrogen atom. Why hydrogen atom is unique compared to other atoms?
It has no neutrons, sir.
That's not the
one electron, sir, like we can apply
only one electron. See, when Bohr was getting Bohr model was being discussed, neutrons was not yet discovered. So see, that's what I am showing you the chronology, the dates, right? So 1809 Dalton model, then you had the next Bohr model in which year? Hello? 1897 electron was discovered, right? Prior to that
1900 Thomson model.
1900 Thomson model, right?
1909 Rutherford, sir.
So electron was discovered in 1897. So there afterwards the Dalton model, we had to scrap off the Dalton model, right? So the chronology is important, and James Chadwick discovered neutron in the year 1935. Am I right?
Yes.
Right? So until then, neutrons were not there. So Mr. Ligade, you have to watch out. Okay. So as Mr. Dimant told now, hydrogen is unique because it has only one electron. Okay. Now in other atoms you have more than one electrons, and therefore the net force acting on the electron is not just because of the protons, it is also because of the neighboring electron. Okay, so then the system will be slightly different. So therefore it is apparent that this model is not entirely accurate when applied to any atoms other than hydrogen atom. First point. Then came the quantum mechanics revolution in 1920s, and it brought along several goodies to the party. Some sentence like this. Firstly, it has to be godly Schrodinger equation, aka wave function, which describe how the system or electrons in this case will change with the time. This is essentially F is equal to m into a in quantum mechanics. It should be noted that this wave function gives the probability of finding the electron where the electron can be located. So Schrodinger's equation is a wave function. Why it is a wave function? Because the mathematical model is similar to the wave function that we have seen. The wave is traveling and whatever function we call, it is similar to that. And what is important is this model will tell us the probability of finding the electron, okay, around the nucleus. Okay. So the next goodie that is apparent that appeared from there is Heisenberg's uncertainty principle. Simply put, we cannot measure both the position and the momentum and hence energy at the same time. It is either one, the other will have a very large uncertainty, or vice versa. You cannot get both values to have low uncertainty. I suppose this sentence is very clear.
Yes.
Yeah. So that is Heisenberg. So you see, these are all the theories by which the atomic model is being discovered. At present it is present to us. Lastly, it is the interpretation of the quantum mechanics result, the Copenhagen interpretation along with the iconic Schrodinger cat paradox. I think you should be knowing about the cat paradox. Okay, if you don't know, I will teach you when I deal with the Schrodinger's equation. You will understand the Heisenberg's uncertainty principle with this model, cat model, and most widely accepted interpretation of quantum mechanics. So according to the wave function of the system, we can get a probability of finding the electron within the selected area, and the Copenhagen interpretation says that when we make any measurement, we collapse the wave function to that specific location. So that's how you are going to get the wave function. When you plot the math model, Schrodinger model, the plot will look like a wave. Okay, so the peaks that are appearing is indicating the probability of finding the electron at that position. So R versus the probability of finding it. I suppose you remember that. Probability versus the radius. If you draw the graph, then you will get the peaks. So the peaks is indicative that it is the probability of finding the electron. Anyway, I will be dealing with all these things in detail. I am just telling you, connecting you with what we are learning now and what we are going to learn next. And since you have already learned, you should not have confusion. Therefore, I am just presenting these things at this stage. So, the understanding now is that we don't know exactly where these electrons are. See, Bohr, we are going to shortly derive the Bohr radius. So once you derive the Bohr radius, when you are applying the Bohr model, then the Bohr radius will tell you where the electron is, at what vicinity the electron is. Okay. However, as I just now mentioned, if it is multi-electron system, then the Bohr model cannot be applicable. Bohr model is only applicable for hydrogen-like atoms. I suppose you have heard this word, hydrogen-like atoms.
Yes, sir.
Other than hydrogen, what about hydrogen-like? Good. Yes. So from helium, if you knock off one electron, then it will become hydrogen-like model. And from lithium, if you knock off 2 electrons, then it will be hydrogen-like model. Okay? Yes. So the understanding now is that we don't know how exactly these electrons are. So therefore, the exact picture of the electrons, we don't know how the electrons are actually moving. But in the elementary level, it is fine. So therefore, we roughly know that it is in that area. But by probing where exactly it is, you actually make the electron to be there by using the equation. Thus, through solving the probability function of Schrodinger equation, we can get the most probable location of the electron. This is where we get the idea of electron shells like SPDF, which the chemists prefer, and KLM, which the physicists prefer. See, I am bringing to the fore all these differences. So in chemistry books, we say SPDF. I suppose all of you know that, right?
Yes, sir.
What are SPDF?
Options.
So S becomes what? S becomes the orbit or orbital? Orbitals, right? So, yes, the shells and all, and we use the similar terms in physics. We use KLM functions. We use these terms, so you should not confuse. They are one and the same. Then that we know of so. So you hear in PU and 11th class that an shell is a sphere. P shell is double shaped, etc. The idea of electrons revolving in circles is still taught only at the more elementary level. That is in the high school level, and now you are in the higher secondary level. So now you have to understand the atom like this. As of current quantum mechanics understanding, the electron is everywhere until you measure it. These are all the golden sentences. I suppose you apply yourself and try to understand this, because as you can see, these sentences are a bhandar for the examiner. He can pick any sentence or word from this and he can coin a question or two in your examinations, in any format of examination. Okay, fine. So, any questions here? Hello?
No question.
Yes.
No, sir.
Okay, fine. Then the next thing that we would like to learn here is, well, the physical variables that get related are epsilon naught, the permittivity of vacuum, Z, the number of protons, E, the charge on the electron, R, the Bohr radius, MP, the mass of proton, Me, mass of electron, Mn, mass of neutron, but mass of neutron will not be there, right, in this case. But I am just showing you here Mn by mistake, as usual, right. So V is the velocity, N is integer. What is the value of N? N is equal to 0, 1, 2, 3, 4, correct?
1, 2, 3.
1 to 3%.
Thank you. So it is only 1, 2, 3, 4. Okay, H is the Planck's constant in the Bohr theory, and the basic path models that we use is 1 by 4 pi epsilon naught ZE into E by R square is equal to mv square. Yesterday we have discussed this, and angular momentum is conserved. mvr is equal to nh by 2 pi.
Yes.
Fine, students. So this is the basics with which now we are going to learn more about the Bohr model. What we are going to learn is now the electron is revolving. Now the velocity of the electron in the nth orbit, right? So what is the velocity of the electron in the nth orbit? So what we will do here, take the basic equation, the force equation, 1 by 4 pi epsilon Z E square is equal to, what did we get here? This is equal to mv square by r, correct? Hello?
Yes, sir.
So you divide and multiply this by r. So here you get mvr, mvr, and mvr is equal to nh by 2 pi. That is what is written here into v. I suppose you understood this.
Yes, sir.
So just substitute that and filter out v from this, and we are going to get this format of the equation. V is equal to z by n bracketed E square by 2 epsilon naught h, and bracket complete, that's equal to, in short, z by n into v naught. Now this is important. I suppose, have you done this sort of equation modeling? Hello?
Sir, when you multiply and divide it by R, then again...
No, multiply and divide by R. See, just understand, it is mvr, okay? Now, here 1 by 4 pi z is, I want mvr to come here. I want mvr to come here. So what is done here? This v is taken away from this. See, there is already an r square here. So this r and this r will cancel here.
Yes, sir. Yes.
Okay, and this r will come here, and you will get mvr here. That is why 1 by 4 pi epsilon z is square here. Sorry, I also told something there. So nh by this. So you will get this format, z by n into v naught. Okay, what is this here? Because now here you see, v naught will stand for what? V naught will stand for
First Bohr orbit.
First Bohr orbit or the ground state. Now it is obvious that in the first Bohr orbit, z is equal to, for hydrogen, z is equal to 1 and n is equal to 1. So whatever remains now is nothing but the velocity in the 0th orbit. And therefore, we will interpret E square by 2 epsilon naught h. We will interpret E square by 2 epsilon naught h as V naught. I suppose this is a good formulation. Everybody got it. Hello, faster.
Yes, sir. Yes.
So, see now therefore, our way of expressing becomes very simple, because the velocity in the nth orbit of hydrogen-like atoms. The velocity of the electrons, hydrogen-like atoms in the nth orbit is z by n v naught. See, if you take lithium, z will be equal to 3 and n is whichever orbit. N is equal to 1 first orbit, n is equal to 2 second orbit. Then this v naught will be what? The velocity of the electron in its ground state. So this is easier to remember, correct?
Yes.
Now if you plug in all the values here for V naught, because charge of the electron is 1.6 into 10 to the power of minus 19, 2 into 8.85 into 10 to the power of minus 12, H is 6.625 into 10 to the power of 34. So you get here 2.1 into 10 to the power of 6. And this is 1 by 137 the velocity of light. So that is 2.2 into 10 to the power of 6 meters per second. See, this is the speed with which the electron is revolving around the nucleus in the hydrogen like atom in its ground state. Clear, students?
Yes, sir. Yes, sir.
Did in chemistry also you had the similar model, or you had something different?
Similar.
So you have also written there Z by N into V naught?
Yes, sir. Yes, sir.
Great.
Yes.
Then my job will be done very fast. You can quickly go into the numerical section. Okay, this is about velocity. And similarly, about the radius. Okay, so radius. The same two equations are used. They are manipulated, and we get here the N. There, see here R is equal to. You can see here R is equal to. We are getting it as N square pi Z R naught, where R naught is the radius of the ground state. As you know, the electron cannot be anywhere. It has to be in the pre-designated vicinity. That is, the radius is R naught, R1, R2, R3, R4, so on and so forth. So get here N square by Z R naught. I hope this is clear, students. Hello?
Yes, sir.
Now you see, these equations that you see here, they appear to be humongous, but don't make it difficult for yourself, because all these equations, the basic two equations, if you remember, these two equations, if you remember, then rest of the things can be derived from those equations. Clear? So automatically you can start deriving all those equations. And what is the value of R naught? What is the value of V naught? You know, it is a matter of just putting it into bracket, filtering out N and Z. So from whatever you are going to get, filter out N and Z, then you are going to get these formats. Okay, friends?
Yes.
So what is important here is, you know, velocity is proportional to Z by N. Velocity is proportional to Z by N. Okay, and V naught is a constant. I suppose you can appreciate this.
Yes, sir.
Similarly, R is a function of N square by Z. R naught is a constant. Okay, and you can see here R naught is 0.53 angstroms, 10 to the power of minus 10 meters. This is slightly involved. See the heading here, the total energy of the electron in the nth orbit. Total energy, mark that. So from equation 1, kinetic energy is half mv square. So so here you see mv square. So what will you do here? You will substitute the value of v from the above. If you substitute the value of v that you have got from above, what is the value of v that you got from above? Z by N E square by epsilon H N. Okay, or even from this you can get the value of v in terms of NH by 2 pi. Okay, in terms of R and all this, you can also derive it from this or from this equation. And when you substitute that here, so you will get the energy, the kinetic energy half mv square Z x square by so and so. Okay, and the potential energy, is similar to gravitational potential energy. I suppose all of you remember that the gravitational potential was minus G m1 m2 by R. So in the case of electrostatic forces, or in the field of electrostatics, the potential energy will be, instead of m, it is q1, instead of m2, it is q2 by R. and this is the potential energy. So if you compare this with this, you will see that the potential energy is twice that of the kinetic energy, or the magnitude of the potential energy is twice that of the kinetic energy. So the total energy of the system E is equal to Ke plus Te minus 2 Ke plus Ke is equal to minus Ke is equal to minus Ze square by 8 epsilon. Okay? I hope you have derived all these things in chemistry, right?
Yes. Yes.
Yes. So it looks humongous, but don't make it very difficult because from the basic two equations you can derive all this. But what is important is the abstractions at the end. So these abstractions matter a lot, because if you are able to abstract from these equations, these relations, they become handy in solving the questions very quickly. So modulus P is equal to 2 Ke. So the total energy of the system E is equal to Ke plus Te, so and so is equal to so and so. Now, as R is equal to so and so, we have En. What is En? The total energy of the nth orbit. The total energy of the electron in its nth orbit. Okay, so you have to substitute all this. So you will get here this equation, where negative side indicates that the electron is bound to the nucleus and not free to leave it. With the increase of n, the absolute value of the energy also increases. See here, with the increasing n, the absolute value of the energy also increases. But I suppose you understood this statement. Hello?
Yes, sir, understood.
So n is increasing here, this value is decreasing, going closer towards 0. But from negative value towards 0, 0 is greater than a negative value. So as n is increasing, this En is approaching the the zeroth value. So that means the potential energy is, the energy of the energy En is increasing as you go away from the nucleus. Correct? What is decreasing? As you go away from. Yesterday, one more thing we had a discussion. What is it?
It is attractive.
Hey, what is decreasing when as you go away from nucleus?
Kinetic.
Somebody said kinetic energy, but something else will decrease. I told you no, the affinity. Yes, Sijan, what are you doing today?
Yes, sir. Electrostatic force will increase.
Today you are keeping quiet. Your throat is okay, no?
Yes, sir. Yes, sir.
Okay. So its electrostatic force will go on decreasing, or in other words, the affinity towards nucleus will start decreasing. Keep that in mind, and that is why they are easy to be knocked out compared to the electrons within the inner shells. Or you can derive this equation by say putting the value of R in this equation. You get here. This again is important. So you get here E is equal to Z square by N square into E naught. So this value we take it as constant here. So here you have to notice that first what did we derive? The velocity. Velocity was proportional to Z by N. Right?
Yes, sir.
Radius was proportional to Z by N square. And energy is proportional to Z square by N square. See, these abstractions are very handy when it comes to solving the questions quickly in the examinations. And this value is also at most important. The value of E naught, that is the energy possessed, the total energy possessed by the electron in its ground state, will be minus 13.6 electron volt. Okay? So what does this mean? Energy of this is minus 13.6 electron volts.
Under hold of nucleus.
Pardon?
Electrons are under hold of nucleus.
Electrons are under?
Hold of nucleus.
I didn't get you. World of nucleus.
The hold.
Hold. What is it, hold?
Sir, he said electrons are under the hold of the nucleus, sir.
No, okay, fine. That negative side is indicating. But what I am telling you is, what does this entire value mean?
Sir. Sir, the energy in the first orbit, sir, it is the same as the energy gained by an electron when it is accelerated through potential difference of 13.6 volts.
No. You are trying to tell me what is the meaning of electron volt.
Sir, the electrons will always have an energy of minus 13.6 electron volts when they are revolving in the first orbits.
ಅದು ಎಲ್ಲರೂ ಹೇಳ್ತಾರೆ. See, you are studied in gravitational potential energy. You remember?
Yes, sir.
What did you learn there?
That work is done against a conservative force if this is the energy possessed.
So,
Attractive.
see, that is why you see that definition I gave for potential energy. You apply the definition for potential energy. So, the potential energy, you remember? So, we had a point. We had a point mass m, and what is the potential at this point, at a distance r? What is the potential at this point? So how do you do that? You will go to infinity, okay, and you will take a unit mass at infinity, and you will start bringing that unit mass from infinity and position it here. And whilst you are moving here, you will ensure that the velocity will not increase or decrease. Hello?
Yes. Yes.
So the total work that you do to bring it from here to here at a vicinity r, okay, is now in the form of potential energy at this point. And by derivation, in the case of gravity, you got it as what? Minus g m by r square, because this m is equal to 1 m. Okay, generally we write the formula for potential energy as what? Minus g m by r. Okay, sorry, not r square, r. Hello friends, did you get it?
Yes. Yes.
So now similarly what we have got? We have got the nucleus. So we have got the nucleus. Okay, and we are talking about the electron here at a vicinity r. Okay. And what is the potential energy of this electron? Okay, what did we get here? K ZE E by R minus. Correct?
Yes, sir.
Same, laying like this. Now, about the ground state, we got it as 13.6 electron volt. So now I deliberately wrote this, and we defined the potential energy of the electron of this mass at this point as the negative of the work done to bring a unit mass from infinity to this point. Okay? Now in the case of electron, we have calculated it to be this. So what does it mean? That means now if you want to place this electron at infinity, what should you do?
Avoid 13.6.
That is what I wanted. Because now this electron is bound. It is bound to the nucleus. It cannot leave the nucleus. So if you want to pull this away from the nucleus, then you have to supply this much amount of energy. Then you can push it to the infinity. That is, you go on doing work equal to this, then you will keep it away and away from the nucleus. Did you understand?
Yes.
Hello, everybody there?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
So this is, see, these interpretations are extremely important. Okay. Anyways, see, I am trying to bring out all these aspects because the questions are probed like this. Because at this point, it's not just enough for somebody to just say, oh, I got this, I put these values, I got 13.6. Now I suppose all of you have got calculator or something to calculate, right? Hello?
Yes, sir.
So you just tell me what is the value of this if you plug in all the values, and don't start playing with this powers of 10. Leave the powers of 10. Simply multiply 9.1 into 1.6 raised to 4 and divide it by 8, 8.85 square, 6.625 square. Only do this much. What numerical value will you get? Leave the powers. What numerical value will you get? Will you get the numerical value 13.6?
No,
Did somebody do that?
no, sir, not yet.
You will not get that. How did you know?
I use calculator.
You use calculator so quickly. Very good. Either balada or the linger.
Yes, sir, yes.
Okay. Anybody else?
No, not yet, sir.
You are getting 13.6?
No, sir. No, sir.
Oh, somebody said yes, sir. He is getting 13.6. Who is that gentleman?
No, sir.
Nobody got. And then this answer is wrong, is it?
No, sir. The unit is different, sir. Unit is different.
Yes, sir.
So, whatever numerical value you have got is what? It is, what will be the unit? Unit will be joules.
Yes, sir. Yes, sir.
You understood? So, here you see the answer is given in terms of electron volts. Okay. What is electron volts? Anybody? What is electron volt? If somebody asks you a question, whatever answer you know, you tell. Come on, try to tell.
The energy gained by an electron when it is active.
Hey, first tell me what is electron volt. It is also another unit of energy.
Unit of energy. Yes.
Joule is the unit of work done and also energy in the SI system. Electron volt is also unit of energy. First of all, understand that. Okay. Now, joule is converted to electron volt. Joule, the work done, the unit of energy joule is now converted to electron volt. Right? So now, what is the conversion factor here?
1.602 into 10 raised to minus
1.6 into 10 to the power minus. You will multiply or divide? See, you got some value there, right? What is the value you got? What is the value you got?
minus 2.18 into 10 raised to minus 18.
Okay, wait. You got here what? Minus 2 point. Hello?
180 into 10 raised to minus 18.
10 it is something. Okay, right. You got 2.8. Numerical value I'm asking. But now this is 13.6. Correct?
Yes.
So now what is the conversion factor from this to this?
Divided by 1.6 into 10 raised to minus 19.
So which one will you divide? This one or this one?
Left.
You will divide, correct? So now try to understand this very quickly. This unit of electron volt, it is the gain in the kinetic energy. Okay, the gain in the kinetic energy of an electron which is accelerated across the potential difference of 1 volt, and the electron must start from rest. Okay, so what it means is, supposing there are two plates and I have connected this to a cell of potential difference 1 volt. I suppose you understood what I have written here.
Yes.
I have taken a battery cell of 1 volt and I have connected between the two plates. Now, if I place an electron here, and of course, I will say this is the ground position. If I place an electron here, then this electron, what happens? See, this is plus and this is minus. So this plate is plus and this is minus. So this plate is plus, that means this is positive, and the electron, as you know, is negative. So therefore, this electron will start getting attracted towards the positive plate. What happens? That means there is force acting on the electron. And due to this force, what happens to this electron? Accelerates. Okay, so there is electrostatic force here, and this electron will start accelerating. Okay, accelerating. And as a consequence, what happens? Its velocity goes on increasing, and therefore its kinetic energy also goes on increasing. And by the time it comes here, the change in the kinetic energy is delta T. Okay, got it?
Yes.
So therefore, and now we say how much kinetic energy that it did this gain? It gained the kinetic energy that it gained is equal to 1 electron volt. Got it? Hello?
Yes, sir.
So 1 electron volt is the gain in the kinetic energy of an electron, which is accelerated across a potential difference of 1 volt, and it should start from rest. So it was initially at rest and it started. I suppose I made it clear to all of you?
Yes, sir. Yes.
Everybody?
Yes. Yes.
Then your good friend said you have to divide this by 1.6. Of course, into 10 to the power of minus 19. This was 10 to the power of some x. So how did you get this factor 1.6?
Sir, because we already know that minus 2.18 into 10 raised to minus 18 is equal to minus 13.6 electron volts.
So that from that, so you did ulta this, you multiplied and divided and you got that 1.6. Okay, fine. So you see, because this was given to you, so you did it. If supposing this was not given, then what would you have done? You would not have done that. Okay, anyway, I'll tell you. But why should you divide it by charge and electron?
So gaining kinetic energy is a potential difference into charge. So
Yes.
Yes, that is good. So potential, see, if you say the potential of this is 0 here, then the potential of this at this point with respect to this is something, and what happens here when it comes here, the potential becomes 0, and it is all getting converted into kinetic energy. Okay, fine. Now I will just explain to you. See, now you are using a battery here, or a cell, as a source of energy. Okay, now all of us have used this in our high school, and we have done some circuits and all. Do you remember?
Yes, sir.
Hello, everybody there?
Yes, sir. Yes, sir.
So here, from the battery, the current will go here, it will travel through the wire, and it will reach here. I suppose all of you know this. And we wrote Ohm's law, V is equal to I into R. I suppose all of you remember this much at least.
yes, sir.
Now here, this V means what? V means this energy source is going to expend. This energy source is going to expend 1 joule of energy for transporting 1 coulomb of charge around the circuit. Can everybody repeat? We say, sir, not 1 joule. Now, if V is equal to 1 volt, if V is equal to 1 volt only this, otherwise it will be V joules. Sorry, see, if the voltage here is V, then this battery cell will expend V joules of energy in transporting 1 coulomb of charge around the circuit.
Yes, sir.
That is the meaning of this.
Yes, sir.
That means now, you see, the analogy I can give you here is like this. I think all of you have enjoyed merry-go-round.
Yes.
You have enjoyed merry-go-round. So now, you see, supposing your mama, uncle, father, somebody, mother, they are making you to play merry-go-round. So what are they doing? You will start from here and they keep pushing. Okay. So that means they are pushing means what? Their hand is touching you and it is moving. So what is that the person who is pushing it doing? What is he doing? Don't say he is pushing. That everybody knows. From physics point of view, what is he doing?
Doing work.
Doing work. F into delta x. But he keeps on doing F into delta x, F into delta x, F into delta x till you complete 1 circle.
Yes.
So total you would have said done F into delta x n times. So the total work done by him is n into F into delta x. Correct?
Yes, sir.
Yes, sir.
So here you see, this much work he has done. This much work he has done means what? This much energy he has expended from his shoulders. this much energy he has expended for what? For moving you, as if you are, say, assuming that you are 1 coulomb, for moving you around the circle, he has expended this much energy. Did you get it?
Yes.
Now here also this is similar situation. Only thing is now instead of your mama there is battery, and instead of you there is charge of 1 coulomb. So this battery is going to expend V joules of energy for every coulomb of charge. Got it?
Yes.
Hello?
Yes.
Yes, sir. Yes, sir.
Right. So V joules of energy per every coulomb of charge. Now instead of V joules for 1 coulomb of charge. Now we have got only 1 electron to move. So how many? What is the energy expended? So V upon 1 into E gives you what? The work done or the energy expended in transporting an electron around the circuit. Got it?
Yes, sir.
Okay, so therefore the amount of work done by this in transporting 1 coulomb of charge is V. Therefore, for 1 electron it becomes EV. That means this battery is expending 1 electron volt of energy to transport an electron around the circuit. Okay, so that is another way of looking at it. Now you see here. Now you see. So here what we are divided by 1 coulomb. Okay, and multiplied it by electron. And what is the charge of the electron? The charge of the electron is 1.6 into 10 to the power of minus 19.
Yes.
Got it? Hello?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
So this unit will still be joules here. So now if you transport this here, that is why you divide it by 1.6, you are able to get the 2.18 divided by 1.6, you got it as 3.16. Got it? 13.6. Did you understand? That is why that division factor will come. Anyway, I will make it more explicit when I teach you electricity. Okay? So that is how that 1.6 has come into picture. Clear?
Yes, yes, sir.
See, I am making sure that you learn everything as we are progressing. No assumptions here, unnecessarily. Yeah, scientists can assume postulates and all, but we cannot simply assume and keep moving forward. So the units are going to be extremely important for us. So that is how the electron volt has come. And yes, in physics, electron volt is a measure of the amount of kinetic energy gained by a single electron accelerating from rest through an electric potential difference of 1 volt in vacuum. So this is the diagram which is telling you what I said. Next comes the period of revolution of the electron. So T is equal to 2 pi r by V. So substitute the value of R that you got from above and the value of V that you got from above. Okay, and then you will get this. Right? See again here.
Yes, sir.
T is equal to n cube by z square T naught. I hope you are appreciating this.
Yes.
First we got V, it is proportional to n by z. Then the next one was what? After V, R. R was n by z square.
S square by Z.
N square by z. And energy was n square by z square.
Z square.
And now time period is n cube by z square into T naught. Right? See, the abstractions are extremely important. Okay. So we get T naught is equal to 1.51 into 10 to the power of minus 16th second. Very, very, very small. Frequency of revolution of the nth orbit. Same here. So this is only inverse of this. So inverse of this. So this becomes what? F is proportional to z square by n cube. F naught. 6.6 into 10 to the power of 50 hertz. Clear?
Yes, sir.
Great. See, since already you have learned there, fine. Now comes this issue. wavelength of the photon. That means now if the electron jumps from higher orbit to lower orbit, okay, then it is emitting excess energy. What is that excess energy? Right? Why did I use the word excess energy? So it has jumped, say, from this orbit to this orbit. So this is E2 and this is E1. Okay, now E2 minus E1. So this is delta E. So this delta E is what I call it as excess energy. So this excess energy is emitted by this electron in the form of a photon. The representation is like this, photon energy.
Yes.
Okay. So here you see the wavelength, that is the electron has jumped from higher orbit to lower orbit, then it is emitted a photon energy, delta E is equal to so and so. So substitute those things, you will get it in this beautiful form. 1 by n1, see here, 1 by n1 square minus 1 by n2 square. And you know at the ground state, now we are working at the ground state. Sorry, we are working, n1 stands for ground state, this for the next state. So this term already we have calculated, it's 13.6 into so and so z square. And I suppose you understood till this point all this derivation.
Yes.
Now the photon energy in terms of Planck, it is quantized. So that becomes hc by lambda. I suppose yesterday I have written this. That is a photon energy. It is equal to h nu. You remember yesterday I wrote this?
Yes.
Nu stands for the frequency of the radiation that is emitted. And here the frequency is what? hc by lambda. Because you know velocity of a wave is equal to, we have studied it as f lambda, if you remember. What is f? What is v? It is the velocity of the wave. And what is f? The frequency of the wave. What do you mean by frequency of the wave? The number of ripples, complete ripples.
Produced by a source frequency.
See, now source is fine, but here you see when you are talking about wave.
It's passing through a point in 1 second.
Passing through a point in 1 second, fine, that is fine. And lambda will be the distance travelled by the wave in one time period. Okay?
Yes.
So that is it. So we used to write it, and here instead of v, we have got c here, and we have got lambda here, and therefore, and instead of f, we have got, instead of f, we have got nu. And therefore, h2 will become like this. And obviously, our delta E is now going to take this form, h nu. And here, h nu, we are writing it as c by lambda. Okay, so that is what is written. Okay, so delta h is equal to h c by lambda. And this is one thing. Now here, you see, in the case of waves also, we have studied this. We got their wave number. You remember?
Yes.
So wave number is 1 by lambda. So we are giving that name. So what is the wave number here? So nu bar is wave number, but wave number is what? So you can read here. Now 1 by lambda is equal to nu bar. The wave number, why is that name wave number there? The wave number of the radiation emitted, that is the number of complete waves in 1 unit length. That means now if in SI system, if you take 1 unit length, what will be 1 unit in SI? 1 meter. In 1 meter, how many complete waves can be drawn? Understand? So that gives you the wave number. That means now, if the
Yes.
see, I don't know now. Aram se think. See, when we write, what is the interpretation of this? That is, if you take a unit length, say 1 meter, how many complete waves can you draw here in 1 meter?
Yes, yes.
Right? That is the meaning of this. So here I am trying to So the wave number will now be equal to 2e in this case. Okay. Yes. Then this quantity m e raised to 4 by 8 epsilon naught square h cube c. So this value is r infinity. This value is r infinity. Okay.
Yes.
That is, see, now I will tell you something about this Rydberg constant. So see here, you can see here r suffix h. R suffix h is 1.09 into 10 to the power of minus 7. R subscript infinity is 1.0973. You can see there. This is 0.96, this is 0.97. So RH is the Rydberg constant for hydrogen atom, and R infinity is the limiting case for heavy elements. That is, other than hydrogen atom, the Rydberg constant is this. Okay, and MR stands for what? The reduction factor or reduction mass. I think reduction mass. Anyway, so RH will be what? See, e raised to 4 by 8 c epsilon naught square h cube. This is R infinity, and you multiply it by the reduction factor. Then you are going to end up with what? You are going to end up with the Rydberg constant for hydrogen atom. So that is the difference between the Rydberg constant for heavy elements and the Rydberg constant for the hydrogen-like atoms. Okay, or you can very well see here that if the nucleus is not stationary, that is, the mass of the nucleus is not much greater than the mass of the revolving particle like electron, then R is equal to R infinity divided by 1 plus m by m, where m is the mass of the revolving particle. In this case, it is electron, and m is the mass of the nucleus. Okay, friends?
Yes, sir. Yes.
So, see, because this is important here, why? Because I tell you, the Bohr atom is for hydrogen only, or hydrogen-like atoms. Okay, and now if you want to extend it for the heavier elements, then there is a modification that you have to do here, and that is what is something that I have told here. For hydrogen, R infinity will simply be equal to RH, but for others, you have to retain it as R infinity. There is a small difference in this one. It is 1.097 for RH, and for R infinity it is 1.096. Keep this in mind, because I have seen one question appear which is based on this. Okay, then of course, so we get this wonderful formula which we often use it, and that's it. It is regarding the wavelength of the photon.
Sir, why does it change?
Pardon?
Why does it change for heavy elements?
See, now the fact here is for hydrogen there is only one proton and one electron. So whatever is happening there, it is because now it is a system. See, it is a system. See, whatever equation we are writing here is for a system. The energy at the N2 level, energy at the N1 level. It is a system because proton is also involved there. Because you see now the forces that are acting there is acting on both the protons and the electrons.
Yes.
Okay, and that is why you will have a small change in the two. This m is only taken for if it is only one electron. Okay, now for heavier elements, this will not just be one, and the number of neutrons will also be, number of protons will definitely be more. So there are some correction factors that has to be done.
Okay.
And one more important thing is, he proposed a relation between the momentum p and the inverse of the wavelength, Planck's constant. So in the wave, when we studied waves chapter, we have used k. I suppose all of you remember.
Yes, sir. Yes.
So k is equal to 2 pi by lambda. Already we have done that, remember?
Yes, sir, angular wavelength.
So here also you see the same concept is used, but here you see free electrons, for free electrons, he proposed a relation between momentum p and the inverse of the wavelength lambda with Planck's constant h. With Planck's constant h as a proportionality factor, that is the momentum and wavelength. I suppose you know this relation. Hello?
Yes,
De Broglie wavelength, man. Hello?
yes,
I'll come to that de Broglie later on. So, see, I am making all these things clear, students, because you see, you have learned waves chapter. In waves chapter also, we have got the wave number, but there we wrote the wave number k as 2 pi by lambda. And now we are using the similar concept here. We use wave number, but here we are using the notation nu bar. Okay, and u bar we simply wrote it as 1 by lambda. Okay, now there was a wave number in waves and there is a wave number here. So what is the relation? So when you go further, you will see the de Broglie will come into picture, because de Broglie solved one problem. While one set of experiments could be proved by taking electron as a wave, and another set of problems in physics could be addressed by considering electron as a particle. Did you get it?
Yes,
Yes,
sir.
sir.
So now you see, so that means now one set of scientists said electron is a particle, another set of scientists said electron is a wave. Now who is right? You cannot have both, correct? So who is right? So de Broglie will come into the picture and say that, well, any entity which has got momentum, can be written in the form of a wave function. So that means now even me, if I am running, my mass is m, my velocity is v, so my momentum will be mv. Now I can be written in the form of a wave function. You have to understand this. It is a wave-like function or wave function, but not a wave. See, if I am running, you cannot say, oh, you are a wave. See, but one thing is common. When I am running, I am transporting energy, and when a wave is traveling, it is also transporting energy. I suppose you remember the definition. A wave transports what? It transports momentum and energy.
Yes.
I am also doing the same. So in this way, we are common, and therefore there must be commonality. So now my energy, I am moving here. I am mass m moving with velocity v. My energy can also be written in terms of wave energy. The moment I model myself as a wave, that means now what characterizes a wave? Most important characterization is the wavelength. Okay, so that is why the world knows him as de Broglie wavelength, right? And what is that? The momentum p of a body, okay, and the inverse of the wavelength. So momentum is proportional to inverse of wavelength. And what will be the proportionality constant? Planck's constant.
yes, sir.
Understood? So that is how you will get h lambda coming there. Okay, and then you can relate it to the wave number of the wave as 2 pi by lambda. So this k is what we use the wave number in when we write the wave equation, a sine of omega t minus kx. I suppose you remember that k. Okay. Anyway, when we write Schrodinger equation, you can see this relation much more clearer. But I am just writing it here because you should not have confusion between two. Okay. See, because this is a problem, you know, the textbooks, the author who writes one section of physics is different from the author who writes another. So both of them will be using different symbols for the same physical quantity, and depending upon the situation, they will interpret it differently. So, but we should be aware. And here you see chemistry also comes. So there they might use another symbol and they might do it the way. They will use it in their context. But as students of first year and second year, you have to battle it out. See, for example, in thermodynamics, the sign convention used in thermodynamics in chemistry is different from the sign convention that we use in physics. Okay, so as far as I am concerned, I am physicist. I will just use one sign convention and I am done. But for you, you have to battle it out. Okay, so I'm just telling you that this is something, and you please remember this. Okay. I just summarized this here. Kinetic energy is equal to modulus of total energy is equal to half potential energy. Bohr radius r is proportional to n square by z. Velocity is z by n, and centripetal acceleration AC is z by r square. So energy depends on n only for hydrogen, because the other quantities in energy equation of electron are constant. The energy levels of hydrogen, because z is always equal to 1 as far as the hydrogen atom is concerned. Hello? So energy is constant because of other quantities of energy and the equation electron is constant. The energy levels of hydrogen atom depend only on the quantum number n. Okay, so here you see the future quantum number, what n he is using it in Bohr model will become quantum number in the future. For the more complicated atom, the energy levels depend upon other quantum numbers also. Just I have mentioned it here. Okay, got it, students?
Yes, sir.
See, you please understand. Oh, the power off. 1 minute. I'll switch on the emergency lights. Overall. Okay. See, I am mentioning these statements because they are handy when you solve the numericals. So, energy for hydrogen will only depend upon n, right? And for other atoms, then it will depend not only just on n, but on other quantum numbers also. Fine, students?
Yes, sir.
Yes.
And here you see, now comes Mr. Chadwick. James Chadwick, a student of Rutherford, won the Nobel Prize in Physics in 1935 for the discovery of neutron. See, this chronology is also important here. Okay, so now we'll come to your favorite section, that is the numerical section. Are you ready, students? Oh, I think it's already time up, man. I said 9:45, no?